Hello, everyone. My name is Ricky. I'm here to present our project towards automatic mapping of pedestrian path networks at scale. So a little bit about me. I am a postdoctoral scholar at the University of Washington. I work at the Pasteur Center for Accessible Technology. My research interest is on computer vision, machine learning, and accessibility and transportation. And I work on use data science approach to solve the problems that arise in practical applications. So sidewalks and pedestrian paths are the key to a healthy transportation network and building a accessible city. And the significance of having a map that details the location and connectivity of sidewalks crossing the earth can be described at different levels. First, at the individual level, traveling on the sidewalks can be challenging to many degrees for many population because of the uncertainty in navigation due to discontinuity in the sidewalks, missing crossings, and unpredictable barriers. And at the city planning level, planners are often impacted by the lack of network data. So they are unable to identify the bottlenecks in the pedestrian layer and make informed decisions about resource allocation. And planners need to know where the infrastructures are, how they impact the individuals, and they need to have some data-driven ways to model how potential changes may impact mobility and accessibility in a particular area. So to provide the answer to the answer to the question that city planners may have, we need to have a map that details the location and connectivity of sidewalks and crossings, so that the planners can have like a data-driven ways to understand how potential changes may impact the current infrastructure and to make the data-driven decision accordingly. And while the automobile road has been mapped extensively, the pedestrian environment or the sidewalk environment have not been mapped. Most cities do not have a geographically accurate map that details the location and connectivity of sidewalks and crossings. They do not show where are the sidewalks or how they connect to each other. And currently, most mapping methods typically rely on human surveyors collection and annotations. And these methods are laborious, typically non-standardized, and very difficult to maintain up to date. So therefore, we need a automated mapping and an assessment system to try to have a efficient and scalable way to generate a map that can be used by pedestrians. So here we present our solution. We developed a scalable and affordable way to produce the pedestrian path data at scale. And our solution can be divided into two parts. At the upper half, we use the aerial satellite image and other globally available data sources to generate gross sidewalk data at scale. And at the lower half, in order to capture the additional information that cannot be easily learned from the satellite images, we use the second system to capture the street level images and use some computer vision models to segment the street level infrastructure and to generate the accurate connecting map. And I will start by introducing our the first subset of our project. And the core idea of our solution is to let the machine do the human work. And then data is the foundation to any machine learning approaches. Unfortunately, currently, from a machine learning perspective, there are no large-scale data sets that specifically target the pedestrian environment. So as the first step of our solutions, we introduce the annotation for the pedestrian environment dataset. Here we develop methods to rasterize the GIS annotations from multiple sources and from multiple geographic areas. And the data we collected in this dataset covers the selected region in those cities, including Los Angeles, California, Belleville, Washington, Quito, Ecuador, Sao Paulo, Brazil, Santiago, Chile, and Gran Valparaiso, consisting of about 1,400 samples and around 2,700 kilometers square land area. And the classes that we included in this data sets include the sidewalks, shown as the brown in this image, and the crossing, shown as the red, and the sidewalk on the bulb, shown as the blue. Those are the three most important classes to understand and describe a pedestrian path network. Because this is our focus, so we map all other classes, including buildings, a row, or vegetation into the background classes, but we can also add it back to the data set with the same pipeline we use. And along with the data set, we present this end-to-end system to infer a connected pedestrian path network graph. We call the system profit, which do the inference of a pedestrian path network graph in 3 steps. And the first step is this, what we call the seeding step. In this step, we use a tool that we developed for pedestrian to do 3 different tasks. First is to use the existing street networks to infer a optimistic sidewalk network, and then also use the existing street network and the proposed sidewalk network to infer the street crossing locations, and also provide a preliminary conjecture of the curb interface locations. And in the next step is where the computer vision part comes into the place, where we use a multi-input segmentation network that train on the data set that I just talked about, a data set to generate the pixel-wise partitions with the aerial satellite image and the street network image tiles. So the network utilizes the information from both the satellite images and the existing, like the rasterized version of the existing street information. And by using both inputs, our model is able to generate accurate pixel-wise partitions. And then in the last step of our inference pipeline, we use the information generated by our computer vision model, and then we go back to correct and refine our hypothesis, which is a over-optimistic hypothesis. By then, we use the prediction from our neural network to try to find a parameterized fine transformation to try to move the nodes and the edges into the correct locations. And upon testing our approach in several small areas, we then use the approach to generate data for several transit agencies for multiple counties. So we generate the data for 6 entire counties in 3 different states, covering around 16 and 600 kilometers of land area, including King County, Snohomish County in Washington, Hartford and Baltimore in Maryland, and Columbia and Monmouth in Oregon. So that was the first subset of our work, but there was challenge here for learning from the aerial satellite image. The first challenge is that the image resolution is often low in some of the regions. We noticed this particular for the South American cities. And the second challenge here is that oftentimes there are occlusions in the images. And in that case, it's very hard for the model to learn from these images and in turn generate a prediction with low confidence. So in order to capture additional information for those low confidence prediction area, we present the second subset of our work, in which we build this prototype of like a on-device automated sidewalk mapping assessment system. So this entire system is built on a low-power portable computing device. It captures the street-level images. Again, use computer vision to segment the street-level images and then generate accurate sidewalk infrastructure and connectivity mapping information. And there are 3 modules here in this prototype. The first module is the hardware system. As I mentioned, the system is designed as a independent add-on kit that's very small in size and can connect to any mobility device, including a power wheelchair or a scooter, for example. and then it uses a stereo camera to capture the street level images, also recording the GPS location while the system travels in the sidewalks. And then we use a computer vision model to try to understand and analyze what's in the scene, and then segment each pixel into a class, represent each different classes. And in the last step, we have our mapping module, which combines the information from the segmentation network, which is the computer vision system, and the GPS location captured by the system, and to generate the mapping information in real time. And here is a demo of the system while we bring it into the real pedestrian environment. On the left, you can see while the system travels in the sidewalk, it maps the location of each sidewalk fragment, also infers width and connectivity. And on the right here, you can see like different infrastructure, including the traffic sign, traffic lights are also being segmented because those are important in measuring the walkability and accessibility of a sidewalk. And this is like a example visualization of the map output. From here, we can see, so the red represent where the sidewalks are, and we can see how they are connected, and the size of the line width, it's representing its width, and then the traffic signs and poles or other identified objects are related to the map sidewalks by their geolocations. And I will further share some results from a pilot study, and this one was done in Redmond in Washington State. Here we try to map this under construction transit station, and here the different colors represent. The red is represent where the system inferred to be sidewalk, and then the yellow is where the system inferred to be missing sidewalks. And in this first example here, as we can see from the street level image, so the entire path has sidewalk and is well connected. So in our mapping outcome, the entire portion is marked as red. And then in places that there are sidewalks, but they are disconnected, sometimes because of driveways, we can see a mix of red and yellow in our mapping outcome. And in places where there is no sidewalks along the entire street, we can see like the entire portion on the mapping outcome is marked as yellow. Similarly, we have another study done in the Bellevue, Washington State. We can see like where there is sidewalk. There are disconnections and there are missing sidewalks. And then in this last pilot study, we conducted a case study with King County Metro, and we tried to use our system to map the same stretch of sidewalk while the paratransit team do the same. And then we noticed that our system is able to reduce the operation time by over 80% compared to like a human surveyor's annotation, while generating results with comparable accuracy and a standardized format. And this is another visualization of our mapping outcome. We produce the data in a standardized GeoJSON format, and then you can directly use as a data layer in OpenStreetMap with tools like Rapid for additional human auditing or modifying. Just a summary. So pedestrian path network data is very important for building a accessible city, but that data is very hard to collect and maintain manually. So we provide solutions that's scalable and affordable, and then it's automated to replace the human efforts. And the data we produce is in standardized open sidewalks format, so it can be easily shared across different organizations or reused by downstream applications. So that brings me to the end of my presentation. You can see our full paper for more details, or you can send us emails if you have other questions. Thank you for your attention.